Today's lecture is from 1.3, which is an extension of graphing. So today we are going to talk about some basic shapes of graphs and how we can change them to move our graphs around in the plane. So these first graphs that I'm going to show to you are ones that I want you to just know on sight. You just look at them and you know, oh wait, this is, like for instance, this first graph, this red line, is the graph of f of x equals c. I mean, c is just representing a constant. And those of you who have played with Desmos before, when you plug in something like this, it actually gives you a slider. So you can slide this piece around to see how my graph changes when I change c. These are just really, f of x is also y, right? So we're looking at this f of x equals c graph, and as I change my c value, right here my c's are positive, and now my c's are going to go below because my c's are negative. So these are just y equals graphs, and what they do is make a horizontal line. That's the first graph that we want to make sure that we know what it looks like. This is a constant function is what we call it. Okay, so the next basic graph that we're going to concern ourselves with, and again, I want you to know these on sight, and if I ask you what does it look like, you should be able to tell me. Okay, so I'm not going to make the tables for all of these things, but you should have an idea. Oops, that's not what I wanted to do. There we go. I do want you to know what these look like. Okay, so the basic graph y equals x, or g of x equals x, right, because g of x and y are interchangeable, is this straight line that splits the coordinate. It splits the first quadrant in half and the third quadrant in half. So, if I wanted to graph some points in my plane, if I made a table, which I'm not going to, but if I did, then any number I picked, let's say I picked 2, then I would get out 2 because I plug in 2, get out 2, right? So that's why all of these points fall on this line, because like if I look at this point right here, well, I tried to click on 2020, but I clicked on 19.8, 19.8. So when I put in 19.8 in for x, I get out 19.8 for y, and that's at any point on this line. The x and y's are equal. Okay, so that's the next graph that we want to know. Okay, so another type of function that we've worked with that now we want to know what the graph looks like is y is equal to the absolute value of x. So this makes sense in context if you think that absolute value, whenever you have a negative number, you take the absolute value of it and you end up getting a positive number. So if I think about that graph that I just had up here, this g of x equals x, I'm going to put them both up here. Oops, well, if I can click on the right button, I will. Okay, why is it being like this? Okay, all right, there we go. Okay, so essentially, if you notice, it laid right over the top of the first absolute piece of the absolute value, right? This wasn't here before, but this was. And so the right hand of the graph just looks like x, right? Y equals x. And then the left hand of the graph is actually really, it's kind of like we write an absolute value function as an absolute value function, but really it's really a piecewise function. It's two linear functions that come together at this point. Okay. So then, oops, took away the wrong one. Let's take away this one. So then I get the exact same thing on this side. It's just that when I plug in values like negative 20 or any, let me just click on this line here. When I click on any of these values, right, I put in the negative value, I take the absolute value of it, and I get the positive number back. So that's why this has this really sharp bend in it. So anything with an absolute value that's linear is going to have a similar shape to this, okay? So these shapes are important because we can alter our graphs to look a little bit differently, but in the end, they maintain some basic features no matter what. Okay? So that's why we want to know what these look like. So these are the most basic of each one. So now I have, let's zoom in here a little bit, make it, so this is y is equal to x squared. Okay, so the graph of y equals x squared, this is what we call a it is a quadratic function because f of x equals x squared gives me a quadratic. And this is the graph shape here is what we call a parabola. Okay, and so it has essentially this U shape is the basic value graph of x squared. And so I can click on some points just to make sure that so if I plug in 0, I get out 0, right? If I plug in 1, I should get out 1, right? Because 1 squared is 1. So if I put in 2, I should get out about 4, if I can click on the right. So when I plug in 2, I get out 4. And then I get the same, right? I'm not really using the absolute value, but when I plug in -1 and I square it, it becomes positive, and so I have the point -1, 1, which is in there somewhere, right? Oh, saw it for a second. There we go. And so this is the graph of x squared. So any quadratic is going to have this same basic sort of U shape. It's just about where it is in the plane when it's not just the basic x squared. Okay, so the next graph that we're going to look at is the square root of x. So you notice when I put the square root of x up here, right, when we talked about being able to tell domains of things by looking at the graph, I can see that my graph is completely on the positive side of x, right, which makes sense because if I find the domain restriction for the square root of x, then my first step is to say that x has to be greater than or equal to 0. So that means that my domain and my graph are only going to show up on the right side, right? It's only valid for positive values. And again, right, if I plug in 0, I get out 0 right here at the start. Let's see if I can figure out what's a nice square number that I can use here. Oops, I don't really want that point to just keep showing up. So somewhere here at 1, I take the square root of 1 and I get out 1. And then somewhere 4 is a really nice number too, right? I can land on that. So then I have the point 4, square root of 4 is 2. And so then the next nice number that I can come to is 9, because that's a nice perfect square. So when I put in 9, I get out 3. And so this one is a very slow rising graph. If I pull it over, right, it just keeps rising up and up and up. So this is the graph of the square root of x. I know it should only be on the positive side because it's only defined for positive numbers. Right? So a graph we haven't talked about a whole lot, but we're going to start getting into it, is this k of x is x cubed. So this is the graph of x cubed, and you notice, right, it's completely rising from left to right, sort of if you think in terms of positive graph. It's rising, and then I kind of have this pause here, and then I'm rising again. And so basically, right, if I take something and cube it, right, if I plug in 0, I get out 0. If I plug in 1, I get out 1, because 1 cubed is 1. So when I plug in 2, I should get out 8. Oops, I didn't. So let's see if I can find it. There we go. If I plug in 2, I get out 8. So I'm going to, let me click on, can I make that point stay? Of course, when I want it to stay, it won't. Okay. So then I come to the other side. Let me pull my graph up here a little bit. And if I look at points on this side, then I'm going to get basically -1, 1 is somewhere in here. Okay, because I plug in -1 and cube it, and it holds its negative sign. So if I plug in -2 and cube it, I'm going to get -8. So let's come down here. Ah, I saw it for just a second there. When I put in -2, I put in -8. So I haven't really talked about this yet, but this is what we actually call our first example, is an odd function. And so an odd function has what we call symmetry with respect to the origin. And basically what it means for something to have, to be odd, is to have basically, if the point 1, 1 is on this graph, right, which we already saw, then -1, -1 is on the graph. If the point 2, 8 is on the graph, then -2, -8 is on the graph. So basically they have the same points up here, exactly the same points here. They're the same piece of graph, it's just that one is sort of like twisted and down. So the other two graphs that I haven't, so that's a type of odd function. I didn't mention that both the square root of that x squared, right, that's what that graph is, and the absolute value of x, right, these are both what we call even functions. And even functions also have symmetry. You might notice that basically if I covered up one half of this graph, right like in the center, that basically this side of it is a mirror image of each other. So this is what we call an even function because even functions have symmetry with respect to the y-axis, okay? Whereas my x cubed graph, which is odd, has symmetry with respect to the origin, which means that I have points that are exactly the same distance from the origin in here and here. So they're the exact same distance, they're just in a different quadrant. Okay. So again, x cubed has this behavior where it's, you know, with these two functions, I'm only covering the top piece of my graph, right? So my range is restricted. In both of those cases, my range is for strictly greater than 0. All my y values are positive. But when I come down here to my y cubed, or my x cubed, I should say, then my domain and my range are both going to be all real numbers. Now I have this zoomed in a little bit, so it kind of looks like my graph is sort of smushed together here, but really it's really spread out, okay, and it'll go on and on forever. Like if that my points will just be way, way, way up at the top or way, way, way down at the bottom, but they do go on and on and on in both x directions, and then as y goes, it's easier to see y than x, that y is going to completely span from the top of the screen to the bottom of the screen. Okay, so now we know our basic shapes. Okay, wait, oh, there's one more. I forgot. This one actually isn't in your book, but I want you to know it anyway. And so this is actually, now I have it written as a rational exponent. Maybe you can see it, maybe you can't, but I have it written as x to the 1/3 power. But we know that x to the 1/3 power is really the cube root of x. And so you notice, right, in case you're curious as to what the domain is on this particular thing, right, this is, it kind of, whenever you see the cube root, it always kind of makes you think, oh, does that have a domain restriction? But it's an odd root. And you notice from the graph itself that my x values cover from one end to the other, right, in this direction, from side to side. And so that means my domain is all real numbers. And so this kind of graph actually sort of looks a little bit like x cubed. It's just that it's sort of like in a different position, right? It's sort of flipped over and rolled onto its side. Okay. But it has a similar shape. And it, I mean, if you think of what x, the square root of x was, let me just put that back up here for a second. It's kind of similar in just that in the positive piece, it's a little bit similar. It's a very slow rising graph because when I'm taking the roots of things, I'm making my y value smaller, so it's very slow rising, but it has a similar shape, but not quite exactly the same shape as the square root of x, and then the additional piece of back here, right? So what's some nice numbers that we can look at points? Well, obviously, if I take the cube root of 0, I get 0, and if I take the cube root of 1, oh, now it shows up again, okay. If I take the cube root of 1 here, I'm also going to get 1. And then the next nice number that I can take the cube root of is 8. So let me see if I can find, oh, it's going to be right there, which is kind of off my screen. Let me pull my graph a little bit this direction. So if I click on 8 here, I'm still off. There we go. Okay. So I get 8, and then the cube root of 8 is 2, right? And then if I come to the other side, right, the cube root of -1 would also be -1. That would be here. Sorry, I changed my... So the cube root of -1 is -1. And then I want to look out here at -8. And when I get out down here to -8, I get -2. Right? That's again because -2 times -2, which is +4, times -2 gives me -8. So I can take the cube root of a negative number. Okay, so these are basic shapes, and I want you to be able to just say, oh, that's a cube root function. I know that it has this sort of a little bit like an S type of thing, right? And it gets a little bit vertical right here in the middle. Now there's a couple more shapes of graphs that we're going to talk about, but we won't talk about those until we get into the rational functions as well. But it'll make everybody's life and yours a lot better, mine too, if you can recognize these basic shapes. So you want to know the constant function, the absolute value function, x squared, the square root of x, and also the cube root of x and x cubed. Okay. So the two polynomials, well actually you got three polynomials, right? The constant function, plain x, also this, so we want to make sure that we know all of those functions. I have x squared in here an extra time. I'm not sure why I have that. We can make that go away. Right, so we have the constant function, we have the absolute value of x, we have x squared, the square root of x, the x cubed, the cube root of x, and plain x, which somehow got moved up here to the top. So we want to know what those are like. If you want to, I mean, I highly recommend that you go to Desmos and sort of play with it a little bit.